So I'm Jaker, and I'll be presenting the paper Reflective Shadow Maps. By the way, feel free to ask any questions that you have in chat or interrupt me at any time in case I forget to look at the chat. So the main motivation behind reflective shadow maps was to have dynamic, real-time, indirect illumination because it's vital in making scenes feel realistic. And the existing methods in 2005 were unable to achieve this as they were either too slow or required baking. So first off, I'm going to give a quick shadow mapping refresher. It's vital to understand basic shadow mapping as reflective shadow maps extend this. The first step of shadow mapping is to render a scene from the light's point of view to a shadow map, which stores just the depth. The next step is to when applying lighting, we project the fragment world position to light NDC space. And then the final step is simply to sample a shadow map using the XY components of the projected coordinate, and then compare the depth of the sample to the component of the projected coordinate. If the sample is closer to light camera, then the pixel we're shading cannot be seen by light, and thus in the shadow. Hopefully I explained that well enough. Any questions on shadow mapping? Okay, I'll move along. So basic couple observations motivate the design of reflective shadow maps. First, we can see that in many cases, one bounce of diffuse indirect illumination is enough to be believable. We can also see that all one bounce indirect illumination is generated by surfaces that are visible in a light shadow map. So you can see that the ground is illuminated, and the bounce from the light on the ground illuminates the walls, the ceiling, and you also see the top of this red block. The light is bouncing off this and illuminating the wall behind it a little bit. And this is all from areas that are visible within the shadow map of the light. I'll give a brief overview of the whole algorithm here, and then later I'll expand on each step. So overall, the algorithm consists of 3 steps. First, we render the scene to the reflective shadow map. This is the same as a regular shadow map, except it contains normals and radiant flux in addition to depth. The second step is computing the indirect lighting at each pixel on the screen. This involves sampling the reflective shadow map many times in a projected local area around the pixel. And the final step is to apply indirect lighting that we computed. This is just as simple as adding it to the final shaded pixel color. So the first step, as I mentioned, is rendering a scene from the light's point of view to 3 render targets: normals, radiant flux, and depth. The paper mentions using a world position buffer to save computation, but these days we're limited by bandwidth a lot more than we are limited by the ALU, so this optimization doesn't really make sense anymore. Secondly, you might be wondering what the heck radiant flux is. According to Wikipedia, I mean several things relating to the amount of radiant energy transported per unit time, which is just a fancy way of saying how much light energy is being reflected from the surface or coming into the surface. In practice, in our case, it's just the light intensity times the surface albedo. Just make sure that you reduce the light intensity by distance and or cone angle, depending on the type of light that you're shading. In my implementation, I have a simple directional light, so it's just the light intensity times the surface albedo. And another thing is that backface culling trick that's often used to reduce shadow acne in regular shadow mapping does not work here because the front face info is precisely what we're exploiting for reflective shadow maps. Any questions about rendering the scene to the RSM? If not, I'll move ahead. Oh, yeah. So the last bit about backface culling. So normally normally in shadow mapping, you render the back face rather than the front face of geometry. This is to reduce shadow acne, pretty much. But here in reflective shadow maps, we need the front face info. So we want to render the front face. Is that clear enough? Yes, because we need to know the albedo or the radiant flux, and also we need to know geometric info such as the normals and the position of the surface, because we're going to be using that in the indirect lighting computation, which I actually discuss in the next slide. Those are the most involved part of the algorithm, which is computing the indirect lighting. First of all, we treat all pixels in the reflective shadow map as an indirect light source. The paper calls them pixel lights. Also, for any fragment on the screen, a pixel light's contribution can be easily calculated. I'll explain that in more detail in the next slide. Third, we'd like to sample every pixel light in the RSM, but a few problems with doing that. First of all, sampling millions of RSM pixels for every fragment on the screen it's not going to work. It's going to be a bit slow. And also, adding all pixel lights contribution will lead to severe light leakage because RSM does not account for geometric occlusion. So a solution to that is just going to be take a set number of random samples in a small area around the fragment. And I'll also show that in more detail later. So here's a big spooky equation we use to calculate lighting from a single pixel light. It's actually not that complex when you break it down. So the paper defines a function E sub p that takes a position and normal of the fragment, whose indirect lighting from pixel light p we want to calculate. Basically, it's how much light goes from the pixel light to the fragment we're shading on the screen. And we're going to be sampling a whole bunch of pixel lights for each fragment. The numerator of this division basically tells us how much two faces point towards each other. So you're probably familiar with using Lambert's cosine law to get the amount of reflected light from a diffuse surface. This is just the same, but for two surfaces, because we're going from the pixel light surface to the surface we're shading, and then from the surface we're shading to our eye. Then the denominator is just attenuating the indirect lighting by distance from the pixel light to the surface. Normally a square of the distance is used, but the paper uses a fourth power because it does not normalize these two vectors at the top. It's just an optimization. It doesn't change the outcome at all. Oh, and then the whole division is multiplied by the radiant flux of the pixel light. And then that gives us the lighting contribution from one pixel light. Hopefully this diagram illustrates it well enough. We have two pixel lights in blue. They're just samples that we've taken. And then the red is the surface that we're shading. So when we go to sample pixel lights in the reflective shadow map, we sample a circular area around the projected pixel coordinate using polar coordinates. The left image is my artistic rendition of the previous scene from the light's point of view. Hopefully that's clear enough. The red dot in the middle is the pixel that we're shading, like the fragment on the screen, and the blue dots represent the pixel lights that we randomly sampled. This view is important because it allows us to visualize where the samples will be taken. And the large blue circle around this whole area in the middle is the area in which we'll sample. The radius of the circle is the scene-dependent parameter, Rmax, which we use to control how global the indirect lighting is. And then this right image shows how important samples may be distributed and weighted. This is the sampling pattern I use in my implementation. important sampling is used because generally we can see that samples closer to the projected fragment coordinate will contribute more light than the ones far away. So it doesn't always work out that way, but it's a pretty reasonable heuristic that the paper employs. And then you can overlay the two images to see which pixel lights will be sampled. Any questions about sampling?
I was just going to ask where you get this pattern from.
That will be covered in the next slide. Yes, so smaller means less contribution, or the sample is weighted lower because there's more samples clustered near the center and there's fewer samples on the outside. But since you're clustering the samples, yeah, you have to weight them. But that's also explained in the next slide. So I'm just gonna go to the next slide. So this is the code I use to generate samples in my implementation, one for one. The first line I use to generate two pseudo-random numbers using a low discrepancy Hammersley sequence. The original paper uses a pre-computed array of random numbers, but I found it to be overkill, so I went into the more simple method. Then the random variables are used to create a single random polar coordinate with radius R max, which is the scene-dependent uniform value. And then the polar coordinate is converted to Cartesian and used to offset the projected fragment coordinate. And then finally, we calculate the weight as the square of the first random variable. This accounts for samples being biased towards the origin by assigning less weight to those. In other words, it's basically the inverse of the PDF. Any questions about this code? All right, I'll move along. So the third step of the algorithm is just applying the indirect lighting. If you store it in a sample, or if you store it in a texture, all you have to do is sample the texture at each fragment and add it to the final color as an ambient term. It's really that simple. Now I'm going to give a quick analysis about the pros and cons of reflective shadow maps. So its main advantage is that it's pretty simple. The core of the algorithm can be implemented in about 30 lines of code. Oh, sorry, Owen, where's the weighting done? Yes, the weighting is done. Basically, the weighting is done after you've calculated this pixel light contribution. Hopefully that makes sense. So you just multiply the result of this function by the weight of the sample.
So that's you'll multiply it at the end here after you've sampled it.
Okay, sorry, can you repeat that?
Like at the end of your code there, you were just loading a sample from a texture, right? Are you then after that doing the like weighting it with like the normal?
Oh, this. Okay, so I do the weight before I store it in the indirect lighting texture. So I calculate so basically right after this code snippet that we're looking at, I use this to get the sample, and then I take samples from the reflective shadow map. And then I use the sample as the input to this lighting equation.
Oh, okay. So so that texture you're sampling from the end, that's like a G buffer, like you've already calculated all this.
Yeah. Sorry for the confusion.
Okay. That makes sense.
It's pretty much just a G buffer, yeah.
Cool,
but
thanks.
you don't have to store it in a texture. You can, if you're doing like forward shading or something, you can just compute the indirect lighting directly without having to store it in a texture and everything. Okay, so back to this. Is everything cleared up with that?
Yeah, that's good for me.
Okay, cool. Yeah, so the main advantage of this algorithm is the simplicity. The core of the algorithm, like the sampling loop, can be implemented in about 30 lines of code which I'd say is pretty good compared to other global illumination algorithms. Then the second advantage of this is that it doesn't require baking. It's a dynamic real-time indirect lighting solution. So, your scene can be moving around and stuff. Yeah, modern hardware, it runs in real time with a bunch of samples. On worse hardware, the samples can be reduced. The number of samples can be reduced to reduce the cost at the expense of indirect lighting quality, which I'll show how that looks later. And then the main downside, well, all the downsides of RSM have to do with it being kind of low quality in most aspects. The main one is that RSM does nothing to prevent light leakage through geometry. It also suffers from projection streaks when a large surface is indirectly lit by a comparatively small number of pixel lights. I'll also show how that looks. And it isn't that bad in most scenes, but RSM only approximates one bounce of a completely matte surface or a completely diffused surface. So it doesn't get you like glossy reflections or glossy GI, and also won't like light up the whole house interior. And finally, there's a scene dependent parameter Rmax, which is used to control the sampled area. It has to be adjusted to fit the scene in a balance between quality and indirect lighting coverage. I will also show how that looks when you adjust it. Now it's time to look at some pictures. So in this image, you can see indirect lighting from the floor on the other side of this thin wall is leaking through the wall, and it's illuminating the other interior wall. In this picture, you can see long streaks on the wall due to vertical strips having nearly the same projected XY coordinate, and then therefore sampling the same area in the reflected shadow map or reflective shadow map. This can be improved by increasing the sample count, but of course that will reduce the performance. And now here's a comparison showing the scene dependent parameter Rmax. At low value, you get accurate local indirect lighting, but when you increase it, the indirect lighting covers more of the scene, but it's a lower quality. So I'll go between the two. Low Rmax and high Rmax. So its value really depends on what you want out of this algorithm. And now here's a comparison showing different sample counts. With just 100 samples, the indirect lighting is pretty chunky. And when you up the sample count to 400, you get a much smoother result. I found this to be a pretty good compromise between performance and quality. And then if you go to absurd 1600 samples, the performance gets pretty bad, but at least the artifacts are pretty hard to notice. So we go between them, 100, 400, 1600. And then also the RSM paper uses a basic screen space interpolation technique to improve performance. So first, the expensive indirect lighting is computed at a low resolution. In this example and in my implementation, I use quarter resolution. And actually we have a series of passes which progressively attempt to fill in the missing pixels by interpolating the neighbors. If the neighbors are spatially similar, we're able to blend them. However, geometry at corners and edges won't be valid to interpolate between neighbors. You have to manually calculate indirect lighting. They end up with a filling pattern that looks kind of like this. Any questions about screen space interpolation? All right, moving on. Oh yeah, here's an image showing in red all the places that interpolation couldn't work. And so indirect lighting had to be fully calculated. As the scene gets more detailed, this degrades to full evaluation for every pixel. But in this simple scene, it's pretty good. There's very few places that actually need to be fully computed. Oh, and that's the end. And also some links at the end. I'll upload this presentation for you guys to look at. Yeah, and I'll also upload the screenshots somewhere so you can see them without the epic stream compression that I'm sure you're experiencing. Because I'm sure that on the stream, this 100, 400, 1600 thing, it's really hard to notice the difference.
The low sample one's quite obvious, but the higher is a little tricky.
Yeah, it's, for sure. I'll upload the screenshots. And I'll link the shader toy thing. There you go. Make sure this link actually works. So yeah, this just shows the image that I use to represent how samples are taken. There's 3 different modes you can choose from. It's uniform sampling. The default is important sampling. And there's also Cartesian sampling, which is not desirable because it samples a square. Any questions about reflective shadow maps?
Do you know if there's any similar techniques that kind of build off this that try to do more fancy things with geometric occlusion and light leakage?
Yeah, as far as I know, reflective shadow maps are used as the basis of a lot of indirect lighting algorithms, but the main one I know of is light propagation volumes, which I don't think it accounts for geometric occlusion. I think it just basically provides of like higher quality, like less light leakage, and it's cheaper to evaluate and stuff. That's my understanding of it.
So I like how simple in concept this one is, and it seems like a really good kind of base level to add first and then improve later.
Yeah, I found it to be surprisingly simple to implement myself. Oh yeah, actually, speaking of which, I'll provide a link to my implementation of that in the chat.
Hey, I've got a question about different light types. I noticed you were using orthographic, directional light. Can you do the same thing with a projection matrix for point lights?
Yeah, you can.
Yeah.
It's very much the same deal. You just
Shadow
have to
mapping.
change. Yeah, you just have to change how you do. Yeah, same as shadow mapping, pretty much.
Yeah.
You just have to change how you sample a little bit.
Very cool.
Actually,
thanks for the links in the presentation.
Oh yeah. The original paper, which I have open somewhere, uses spotlights. Yeah, like in this picture, it's pretty obvious. So it's a spotlight.
Yeah.
I just use directional lights because it's simpler.
I wonder if does Cascades make a difference? You could do cascaded shadow maps. Does that make a difference in this?
Sorry.
Like, is so with shadow mapping, you can use cascaded shadow mapping where you take
Yeah.
larger. I wonder if that has an impact with using reflective shadow maps, or is it just? I'm not sure that it's beneficial. I'm just trying to think through whether using cascades would be beneficial in this instance.
Oh, well,
It's beneficial for resolution and in shadow mapping specifically, but I don't know that it's important.
I don't see why it wouldn't work. I think it would work just fine. I think it'd give you the same advantages that it normally gives you in shadow mapping.
But I guess with the random sort of sampling, it blurs the detail a bit, right?
Yeah, you'd have to account for the size of the projection with the Rmax parameter.
Yeah.
Because that's pretty much an NDC space parameter, which means at higher cascades, it'll increase the radius of the the sampled area. So you'd have to do something to account for that.
I'm definitely going to try this. Sorry, you go.
No. You finish what you're saying.
I was literally just going to say I'm excited. I want to try it out. I'm gonna go and write myself. I'm going to go and fail at some RSM today.
What I was gonna say is, I've seen this technique taken like a little bit farther, where they use the RSM to generate virtual point lights, and then they generate like RSMs for those virtual point lights, and that's used to simulate like secondary bounces.
Interesting.
That said, I'm sure that would probably kill your GPU after so many bounces.
Yeah, I wonder how they do that. Sorry?
I was just going to say that would, if possible, like if it didn't explode your GPU as discussed, would actually solve some of the light leakage as well, right? You'd be able to get.
Well, there's also another NVIDIA's VXGI, when they're injecting the irradiance for point lights, the way they do that to get the irradiance like into the voxel structure is to generate an RSM for the point light, and then that voxel structure, like in addition, like in addition to being used to propagate light, can also be used for occlusion as well.
Sounds super expensive though. What's the trick?
I'm not quite sure. It's NVIDIA's thing, and they got the demo on their website, and they got the source code.
NVIDIA Magic. I'll have to look it up.
Yeah, it's just VXGI. It was all the rave during the Maxwell era.
Yeah.
And only maybe like 1 or 2 games shipped it.
Interesting.
That actually reminds me, I was wondering if you or anyone knows of any games that use this specific technique, because I'd be interested to check it out in practice.
Apparently it's used in some older games. I saw in a thread somewhere. I didn't really pursue that too much.
I think Gears of War 4 was actually using it like for the flashlight, like in some sections, but I could be wrong.
Oh yeah, I did hear that it's used for flashlights.
Which makes sense, Yeah, they're not that bright, and so you're not going to notice the lack of secondary bounces. Yeah, like HCI is actually really cool. You can also go ahead and use it and you can also extend like the use of that voxel structure for even things like area shadows and whatnot.
Yeah, voxels are super cool.
Yeah, I remember the moon landing demo.
Yeah, the moon landing demo was actually nice because they also did something. They they did ray tracing on a 980, but essentially what they did was they rendered a visibility buffer like in a shadow map, or and they were just tracing rays through it. But of course, all that doesn't matter now because NVIDIA has ray tracing hardware.
Do any of you know if there is like a standard real-time GI technique used that's not ray tracing? That's like, I feel like I haven't really heard of a single.
Are you talking
technique.
about you mean like baked or dynamic?
Dynamic?
Oh, well, yeah, that's kind of the thing now, isn't it?
Lumen.
Yeah,
Yeah.
Lumen actually, yeah.
Well, but that's like, I don't think anyone really uses that yet. Right?
Yeah, that's
I'm curious
still,
what like the state of the art, well, not state of the art, but the like standard technique, if there is one.
It's just like there really isn't a standard for real-time GI and games, just because it's something that's not really like affordable yet. Yeah, at least on like
Yeah.
a large scale.
and when
sorry.
you can, you bake.
Yeah. I mean, like you may have like those like one-off sections, while like in like Gears of War 4, where they do like a flashlight, but that's it. Oh yeah. Crisis 2 and was using like light propagation volumes, and the recent Crisis 1 and 2 remakes, they're using Crytek's sparse voxel octree like global illumination, and that's all dynamic. So there are games shipping with it. I think they even got it running on the Switch.
Yeah, that Crytek stuff, that's something I keep seeing, or like I feel like I've seen a lot in the last 10 years. Or, that kind of style of GI in solution.
Yeah. Like Crytek was like pushing a lot like in the early 2010s for like no baking. And
Yeah, like all
enough.
these all these techniques look really interesting, and it's more just like I want to know if there is a single one that these all kind of lead to that's used today, but it sounds like maybe it's more of an ad hoc thing that you have to pick the right one for the right job.
Well, I mean, like we don't really have a standard way of doing GI in games because one, it's very expensive, and two, you kind of have to play it by ear, because it's kind of like situational. It's like what is my frame budget? What is my art style? What is the caveats of this effect or like over this technique over this one?
Yeah. What are you willing to trade off in terms of correctness? Yeah.
Definitely. Actually, the recent I don't want to say remaster yet because we have, since the game was only like 2 years old, but but like the recent update to like Metro Exodus, like they added just full on like ray trace global illumination, and it runs like it,
Yeah, it runs fine. It runs fine on
like it's on PS5 and Xbox Series X, and it runs fine enough. So like it's not 4K, but it runs. And then you got your lumens and whatnot.
Yeah, it might be a good idea. Maybe I'll just look at what both Unity and Unreal do and see. Just mostly out of curiosity.
Oh, RSM uses TA to convert. Yeah, like something I noticed about like the low sample counts of like of the RSMs is that it looked like banding. So I was just wondering if you could like if you could do like a stochastic sampling.
Like this effect?
No, well, if you go to like your where you were comparing like the different sample counts,
The banding might be stream compression. It looks really smooth on my screen.
No, like can you go to like the low sample count?
Yeah. 100.
Yeah, like you see how there's like bands and like the artifacts of like the rendering.
Yeah,
of,
like the big
sampling.
splotches.
Yeah, and I was just wondering if you did like a stochastic sampling and then you like accumulate it over time. If that could
Maybe
be
you
like,
could actually just rotate the filter, right? The sampling instead of being completely stochastic,
yeah, that is
Oh, I mean, like
true.
rotate it per pixel or rotate it over
like
time?
per sample or per pixel. Yeah. I don't know. That way you're not going to get lines anymore. You'll get like, it'll be a little bit
Noise.
more randomized, right? But you
Yeah.
get the same.
Yeah, I did consider that, but I didn't do
You
it.
just
Got
let it
lazy.
like, fair enough. And then they just let it like converge over time, and yeah, fair enough. I also think another way you could like augment this with ray tracing is to like use rays to like test for like occlusion, like to minimize like light leakage.
Hmm.
Because I guess this might be nice, like in the sense that you don't have to write like that you can use this for like a single bounce, and you don't have to like rewrite like all like all your material shaders for ray tracing. I don't know, I'm just talking out my ass.
I'm trying out the random, or I'm gonna try out a random rotation per pixel real quick. See if it actually gives good results.
I wonder if you could talk a little bit more about the that interpolation scheme you were talking about.
Yeah, so what do you want to know about it?
I guess so. This is like frame to frame. You're doing these offsets, or what's happening
Oh,
here? I guess.
this is within a single frame. So I do the expensive full calculation of the lighting in a quarter resolution. So like these green dots basically. So it's really sparse. And then after that path, in another path, I try to interpolate the green pixels to create new ones pretty much. And I compare the position and normal of the green pixels to the red pixel to see if they're valid to interpolate.
Oh, okay, cool.
Yeah, and then I just repeat that 2 times to finish the grid.
So
Because
if
I'm
they're not-
doing something with offset, reduced resolution stuff like that. But it's a little different.
So are you like resampling if it's not valid to interpolate, or?
Yeah, so I can show you my actual code. Zoom in a bit, kind of stream's gonna be really crunchy. Let's see where I do this. Oh, right here. So if the current path is 0, which is the first path, I compute the indirect irradiance from scratch. But if the current path is 1, 2, or 3, I have some offsets. Yeah, and I do something similar to, I don't know how to pronounce it, the a true algorithm that Leslie presented last week. I do that to determine the weight of each neighbor pixel. And then if the accumulated weight is less than some magic number, which means there isn't enough valid neighbors to sample from or to blend between, then we compute the indirect irradiance from scratch. Otherwise, we just use the neighbor colors divided by their weight, accumulated weight.
That's cool.
It's probably a little bit more complicated than it needs to be.
So I wonder,
But
does that
work.
does that actually save you any processing time? Because isn't it still going to
Yeah,
go? Oh,
I
I guess it
measured.
saves you a. Does it save you like texture lookups or something?
There's that 500 samples that's gonna happen.
Yeah,
on that.
Oh,
this
yeah,
compute
right,
indirect
right.
irradiance is
Oh,
500
right, it's
samples.
huge. Okay.
Yeah, so I should have mentioned in the slides, but it does save me roughly half time doing this. So it's a pretty good optimization. Yeah, I was adding the rotation. Let me just copy this real quick. Whoa. Okay, I'll have to take a screenshot and share it in chat. I know it's going to be really crunchy looking. It looks really interesting though.
I'm not sure if you combine that with like some TAA, it'd probably look all right.
Yeah, I can see this. If you converge this over time, it'll look, or if you accumulate this over time, it'll look a lot better. Because this is only 100 samples, which in my slides, it was really bad looking, really big bands and big splotches on the wall. But in this, it's just noise, which is arguably better, especially if you apply some sort of denoising to it or accumulation. So I'll just share an image in chat so you can see it without compression.
Yeah, like I definitely feel like if like a game like were to do like RSMs, why they probably just go with like, I guess the noise approach.
Cool.
Is it just the video compression, or is the noise pattern there staying kind of constant as you moved around?
Oh, it's constant because in the implementation I just did, it's based on the fragment position pretty much.
I see.
So here's
Mm,
just a
Yeah.
random function, and then the input is the global invocation ID .xy.
Oh, I see. Yeah, yeah. Okay.
Yeah, let's make it a little 2x2 matrix.
What if you randomize it per sample?
Well, you could do
Well,
like the world
Or would
position or
that?
something.
No, it is per sample already. Never mind. Sorry.
yeah, Hammersley already gives me a nice circular sample pattern.
Or if you could do the I don't know, can you do the rotation randomly based on the world position or something? I don't know. Instead of screen position.
Looks like the color information's been lost.
Maybe. Yeah, maybe I could. Let me just copy paste another rand function real quick. Oh, this one looks beautiful.
In the screenshot that you posted, the PNG, you can't really see the red reflected object on the back wall.
Oh,
Looks
that's
like
right.
there's a bit of red there.
It looks like there's the slightest hint of red on the bottom part of the shadow on the back wall. Like what I'm seeing on Zoom, it compresses it, but what I'm seeing on my monitor, it feels like there is just a hint of it.
yeah.
So it's not very present, I will say.
So like I'm sure if it could like converge, like you'd probably see more red.
What about reducing the Rmax?
The what?
Sorry, Rmax, the the scene
yeah.
dependent parameter.
Yeah, so I have that as a dynamic thing in my code. So the bar,
Oh,
nope,
cool.
nope, not that one. Oh, yeah,
Oh, ooh.
I reduce a bunch. It's get like super exaggerated. It looks pretty bad if it's too low.
It's an interesting effect.
Sure, screenshot of that. Oh, I have the default Rmax absurdly high for some reason. That's why the previous screenshot looked weird.
Yeah, that's much more like I'd expect with the noisy pattern.
Yeah.
Another thing that just came to mind is if you could like decouple the RSM, like G buffer. I mean, so like resolution from like the resolution of the depth buffer that you're using for shadowing, because since it's just meant for like
Increase the RSM resolution.
No. Like just an idea I had, you know, so like to keep like the actual shadows crisp, way up like to save, I guess on like G buffer size or whatever for the RSM, if you could render like the G buffer of the RSM like at a lower resolution than the depth map for
Oh, I see.
for the shadow. Because I imagine it probably doesn't have to be as high res as the actual shadow because it's just being used for a diffuse bounce.
Yeah.
Right, which is pretty low frequency or low detail.
Yeah, you'd have to render the scene an extra time, I think, for that, but
It is true.
I do agree, probably want to have a separate shadow map for actual shadows.
Because I'm sure like once you start going to like the more absurd like shadow map like resolutions of like 4K squared, you probably don't want to render your your RSM that high.
Yeah, that destroy your bandwidth. So I try randomizing the sample based on the world position. I'm not sure if I actually did it right.
That noise function may be too low frequency or something.
Oh, that could be, yeah. Yeah, if
I
it's
was
in
expecting
NDC.
something different. I was expecting any like microscopic shift to completely change it.
Yeah, because I think it might. Yeah, because if you're in the NDC, it's a pretty small cube. Wonder if you scaled down the world position or scaled up the world position, maybe.
Yeah, just multiply it by a really small number.
Or no, yeah, that's good.
Whoa, okay, that's
Yeah, you can still see the noise
Interesting.
pattern. Yeah.
yeah, I'll share that one in the chat. It's very interesting looking pattern.
It's weird. It looks like reflection off the surface of water or something. Almost
Yeah,
on the ceiling anyway.
Looks glossy.
Reminds me of very low frequency noise. Is frequency the word for it? Like you can
Yeah.
see the pixel grid
Yep.
that the noise is coming from.
Yeah.
It looks, yeah, it's like a really low res texture.
Just
Yeah,
do
it's
like
like-
1,000 or something.
1,000? Okay.
Yeah.
I feel like at a high enough value, it's gonna, like, just moving the screen is gonna shift the world position such a small amount. Oh yeah, moving the screen. I don't know if you can see it, but when I move
Oh,
the
yeah.
screen, it changes
We
everything.
can see
Right,
it.
yeah, right.
I'll do 1 million.
Oh, that's-
Oh, he's actually gonna do it. Lie. What a mad lad.
I think that will blow
Oh.
up the floating point maximum or something.
Oh,
Start to get
definitely.
anything. Yeah.
That's not looking all right.
500 might be a stable number. Oh no, it
Alright.
shifts as I move the screen around.
Probably 50. If you don't mind.
At 50?
Yeah.
Yeah, that was the original one I tried, I think, or
I
one
thought you
of the
tried
original ones.
5.
Yeah, I think
Oh,
like,
right,
like if
okay.
you did 5, you'd see even bigger splotches.
Yeah.
Yeah, I guess there's not enough like resolution and world space coordinates for it to work properly.
The interesting experiment though.
So you think you'll like pursue this further? I can do like I can do like temporal accumulation, or are you just gonna leave it at this?
I think I'll probably leave my implementation at basically the simple thing it is now,
Fair enough.
but I might try improving this further, although I have been advised in the past to not bother with improving this because there's other algorithms that are higher quality. But I don't know, I kind of like simplicity of this.
What other algorithms are you investigating or interested in?
Sorry, what was that?
Sorry, what other algorithms are you interested in investigating?
Oh, yeah, I'm interested in light propagation volumes.
Mhm.
That actually builds directly off reflective shadow maps. That's the main one I can think of now. All the like path tracing techniques are well, considering that I'm using OpenGL, I don't have hardware acceleration exposed to me for ray tracing.
There's the Surfels thing that came out not too long ago.
Oh, I saw that. That seemed ridiculously complex.
Wait,
There's a lot to it.
Are you talking about like Surfel based GI?
Yeah.
Yeah.
Why? That's been around for a while, at least in like the offline space. Though I did see that EA is doing something with it now.
We
There was some
talked
real-time
about it in
thing.
detail
Yeah,
a couple
yeah.
of months ago.
Yeah, we
Oh,
watched
yeah, we
the
did.
presentation or something.
Blew
Yeah,
my
we watched my
mind.
presentation.
I think I made this comment at the time. It's actually kind of funny that like Surfels are kind of coming like full circle because like the first known mention of using them for GI was in GPU Gems 2. And their main like in the main proposal was for ambient occlusion, but the author had put a bit at the end saying, oh, and you could also use it for like for like indirect lighting. And then I guess like the offline movie world just kind of like took that technique and ran with it, and it was kind of like the mainstay when you like up until like path tracing, kind of became like the main thing that industry.
Yeah.
I'm actually gonna link the GPU Gems 2 article. Where is it?